Hello students, welcome to CSDC. So we will start our today's session. It will be continuation of measurement of length by indirect method. Today we will do one very important method called parallax method. First let us try to understand what do we mean by parallax. You see, in case you have an object, you place that object at a very far distance from you, then you observe from left eye by closing the right eye, then you see from right eye by closing the left eye, you will see that the object as seen by you changes with respect to background. Like suppose this O is an object, you are seeing from this L left side with the left eye open, the background would be here. So you extend this, so you will be able to see, suppose X is the background, so you will be able to see X. But when you are seeing from R, then the background will come to I, and so you will be able to see this area of the background. So when seen from different positions, when we are seeing from both the eyes but from different positions, then also we will see in this manner. So this is called parallax. Now when I am seeing from left side, from this side to O, then my light ray is going in this direction. When I see from right, it is going in this direction. So angle LOR is called parallax angle or parallactic angle. So this is angle theta. This angle theta is parallactic angle or parallax angle. Okay. So when we are seeing a far off object from two different positions, then this angle gets formed. Is it okay? Now, if we can, so what is the value of this angle? How it is related to various terms? LO or RO is called radius. Like from O as the center, you make an arc of a circle with OL, or I have written here S, with S as the radius. So this will be the arc. Okay. So this would be the so with O as the center, and if you make an arc, the arc may come like this. So we have learned, if we know the angle, if we know this radius, so radius is S, then arc length is L to R as shown in red, and LR is the chord. So if S is very large, then the difference between these two lengths would be very, very small or negligible. So as we have defined that angle theta in radian is arc length upon radius. So by this angle theta, which is parallactic angle, is arc length upon radius. Arc length is how much? This distance B I have written here. So this is my arc length. Because this chord and this, there is hardly any difference. When S is very large, so this is B, and S is the radius. So, or I can say S is equal to B upon theta. So this is the formula I have got, because I wanted to find how far away is the point O from this location. So that S is B upon theta. B is the basis. B is called basis. This chord length LR or B or arc length is called basis. So this is basis, and theta is the parallactic angle. So in this manner we will be, employ this principle of parallax in measuring various things. So in nutshell, what you have to learn? that theta is arc length upon radius. Theta is arc length upon radius. When we are observing, this is the angle theta, parallax angle, and what is its value? Arc length is this basis B, and S is the distance of the point O from L. So theta equal arc length upon radius or basis upon S. Okay. Now we'll apply this now to find distance of moon or any planet. So let us try to see how we can employ or use the principle that I have explained right now. Okay. For that I will first show you in the diagram. See, this is, I have drawn Earth, full sphere. I am standing somewhere here at point A and I am observing P. This is the planet or moon that I am observing. So from A I am observing, so my line would be AP and distance is S. This is the distance S of the planet from the Earth. Now I will observe the same planet from some other point which is quite far away from A. So I am observing from B. So my point would be BP, and this distance is also S. Because I know that P is here, so I have taken some distance approximately. I have travelled on both the ends, and so these are my S. Now, and so this angle is my parallax angle. Now how to measure this angle? So what I am doing, from A, I am observing a very far away point which I am calling star S dash. So I am observing this S dash which is very far away. So when I am observing from this far away, I will call that as 0 degree in my instrument telescope, and then I will rotate the telescope so that I can see the point P. So I am measuring angle S dash AP, which I have written here, S dash AP. So this angle I am calling phi 1. So this angle is my phi 1 angle. So this angle is my phi 1. So I am measuring this angle. So once I measure this angle, now I will go to place B and measure see the same planet and measure that angle. So I will get this angle. So this angle I am calling as phi 2, measuring from second place. Now for the S dash, whether I see from A or B, it will remain same because it is so far away that there will be no change in observing S dash from A. So that's why I have drawn this parallel line. I am observing the same star. Now by geometry, this phi 1 is equal to this phi 1. This is phi 1, this is phi 2, this will be phi 2. Alternate angles. So that's what I written here. S dash BP is equal to BPR. S dash BP is equal to BPR. So this is phi 2, this is phi 2. Okay, and this is phi 1, this is phi 1. So my parallax angle would be phi, which would be phi 1 plus phi 2. So that's what written here. Phi 1 plus phi 2 is my angle. So now I know this angle. Now basis is AB. Basis is AB. Angle is this theta. So I will be able to get S. S equal to B upon theta. As derived in the previous slide which I have shown you, we get S equal to B upon theta. Isn't it? Theta is arc length opposite, so S is equal to B upon theta. So I know B, I know theta, I can calculate S. S means the distance. So I know this theta now, this full angle is theta, phi 1 plus phi 2, and S I wanted at how far is the planet from the Earth. So I am able to get B upon theta because I know what the distance between the two places A and B, chord distance. Is it all right? So this is one use I have shown you of this technique, parallax technique. So in this manner we have by measurements indirectly calculated distance of planet from the earth. Okay, now we will employ the same technique to measure the distance of the nearby star. When I say nearby star, it means less than 100 light years. So in case the star is 10 light years away, 50 light years away, up to 100 light years away, we can use this parallax method. For that you see this figure 2. It is similar. Now this blue at the bottom is the sun. This small e is my earth. So my earth is rotating in this orbit in the blue color around the sun. Now understand carefully. Suppose I am starting, earth is from A, earth is going to B in this manner. Okay, so earth is moving in this manner. So what is the distance from sun to earth? Sun to earth, what is the distance? That distance we call it 1 AU. So distance of sun from the earth, so E to sun is 1 AU. Similarly from sun to E is 1 AU. So if I take across the diameter of this orbit I am getting, so that will become 2 AU. So the chord AB, it becomes the diameter of the orbit of my earth, which is 2 AU. Okay, so this information would be required. That now you see, from A I am looking at this star S, and as in the previous for the planet, now I will look at a very distant star. So from E I am looking at a very distant star, and so in the same manner I will measure this angle. What is the angle of the star from the line joining to the very distant star? So this angle I have written is phi 1. So I got this angle as phi 1. From this phi 1, by geometry this will be phi 1. If I am drawing a line vertical parallel to this. So this is also phi 1. Now what I will do? I will wait for 6 months. So after 6 months, my earth which was here will come at B. So earth which was at A has come to B. Now I will again look at the same star with very distant star, same, and which is very far away, and so this angle I will call it phi 2. So this is my phi 2, so this is my phi 2. So my angle A star B becomes phi 1 plus phi 2. So this is my theta, I am calling it theta. This is my theta angle or parallax angle. So I measure this parallax angle, and basis is AB. And I have explained to you that AB is 2 AU. So I know basis, I know theta, so I can calculate S by the same formula. S is equal to 2 AU upon theta. So what is my S in this case? S is equal to 2 AU, which is nothing but basis. Okay. So this is 2 AU upon theta. So theta I should put in radians, be careful. So theta is in radians, I will get AU value you know, so I will be able to get the value of S, how far the star is from the earth. Is it alright? So as I told you that this method of finding how far is the star from the earth is for nearby star, which I defined as less than 100 AU, which I defined as less than 100 light years, which is less than 100 light years. Now in case the star is more than 100 light years, then we will use another method, and we will be using a principle of inverse square law of intensity. So we will be using inverse square law of intensity. This law says that intensity of illumination at a point is inversely proportional to square of the distance from the light, I mean from the star, you can say. In this case, my light is coming from the star. So, in case I am getting less intensity of light, means the star is far away. Okay, so intensity of a illumination at a point is inversely proportional to square of the distance. So, what I will get formula? I1 upon I2. I1 is intensity. I1 upon I2 is equal to R2 square upon R1 square. It is inversely proportional, na? Because more the distance, less light will travel. If you have got a bulb, suppose this is my bulb, light source, this is my light source, this is giving light. So, more the distance, less the light, less will be the illumination. So, my formula becomes I1 upon I2 is equal to R2 square upon R1 square. So, knowing from the distance of near star how much illumination we are getting, I can calculate the other one. So, I know I1 and I2, light coming from star whose distance is known, whose illumination is known, whose radius is known. So, I1 and R1 are known, I2 I know I2 how much light I am getting, so I can calculate R2. So, this is how we work to calculate the distance of distant star. Okay. Now, we will do one other measurement. This, now we are doing it, measuring distance of planets from Earth. One method I had told you, now this is the second method. So, in this method there are two sub methods. One is for inferior planets and one is for superior planets. Inferior planets means planets which are closer to Earth than Sun. Means Sun is here, Earth is here. So, the planets which are in this distance, they are inferior, and planets which are in this area here, in this, they are called superior planets. This you might have definitely studied in your geography in your 10th standard. Inferior planets and superior planets. Now, see, for this I am making one assumption which is not fully correct, but we get almost correct answers, that planets are rotating in circular orbits. Instead of elliptical, I am assuming planets are rotating in the circular orbit. So, this is my Sun. This is the orbit in which my planet is rotating. P means planet. So, planet is rotating in this orbit, and outer circle is for Earth, because this is a matter for inferior. So, planet is between Earth and Sun. So, this is a planet, this is Earth. So, in this orbit Earth is rotating, in this orbit planet is rotating. Now, suppose the planet is here where I have written P, this is the Sun, so join S2P. So, now this is a circle, so I have drawn a tangent. So, tangent cuts here. So, if I join P to E, if I join P to E, then my Earth is here. This is my planet. I have just joined P to E. Listen carefully again, I will explain again. This is the Sun. At some particular point of time, Sun was here, planet is here, and Earth is here. Join S to P. Join P to E. Join S to E. So I get this triangle. In case my PE happens to be perpendicular to PS, or you can say PE becomes tangent to this orbit of the planet, then this angle PES is called, which I have written here, epsilon. So, this angle epsilon is called angle of elongation. It's angle of elongation. So what I have to do? Regularly I will measure this angle. I will check whether angle HPE is 90 degree. So on the day when this is 90 degree, then I will measure this angle epsilon, and that I will get angle of elongation. Now it will become mathematics to calculate the distance of planet from the sun or planet from the earth. Is it all right? So now I am doing when this has become 90 degree. So this is 90 degree. So my PS, so this I am calling it RPS. This is the radius of planet rotating around the sun. This is RPE, means distance of planet from the earth. RSE means radius of the orbit of earth. RSE, or distance from sun to earth. This is distance from sun to planet. This is the distance from a planet from the earth. So I wanted to calculate this. Is it all right? Now, when this becomes 90 degree, you take sine epsilon naught. What will be sine? Opposite upon hypotenuse. So opposite is PS, means RPS. So I will get RPS upon S2E, which is 1 angstrom. So my sine epsilon naught. So what you will get? Sine epsilon or sine angle of elongation is R P S upon 1 angstrom. This is 1 angstrom. So my sine epsilon naught is RPS. So I am able to get, so sine epsilon, so this, take it here, so you get so many angstroms. Sine epsilon naught into 1 angstrom is RPS. That's what I have written here. RPS is equal to sine epsilon into RSC, but RSC is 1 epsilon naught. So my distance of planet from the earth is sine of epsilon naught, sine of angle of elongation into 1 multiplied by 1. So multiplied by 1 so need not say. So the sine epsilon naught A loop. And in case you want distance of planet from the earth, then you take cos of this. You will get that answer. So distance of planet from the earth would be this. This was distance of planet from the sun. Is it all right? Then for superior planets, planets which are here, so for that we use Kepler's third law. This will be learning in the chapter of gravitation in 11th standard itself. At the end of the first term, towards the end of the first term we will be learning. So we use Kepler's third law of planetary motion, which says that sun, this time period of revolution, each planet is taking some time to revolve around the sun. So that time is called time period for when it makes one complete revolution. So it says time period of revolution of planet is proportional to cube of semi-major axis, because if they are rotating in this, so this is semi-major, this is major axis. So if I take half of it from center, so this will be semi-major axis. So it is proportional to, see, if the semi-major axis is more, so means it will take more time. Therefore, it is directly proportional. So what you can say, T square is proportional to A cube. This you should learn. What you will learn? T square is directly proportional to A cube. So this is Kepler's third law. We will use this third law and we will calculate. So from here we can say T1 square upon T2 square is equal to A1 cube upon A2 cube. Is it all right? So this is the various calculations. Now we will do last calculation, which is very simple. This is my earth. I am at point O. This is the moon. So I am observing moon from O to A at one end of the moon. And then I will move my telescope and observe the other end B. So this is called the angle which this theta which is called angular diameter of the moon. So this is theta. And I am interested in finding S. I know S means distance of the moon from the earth, that we have calculated by other indirect methods. So I know S, I know this theta angular diameter, so I wanted to calculate the diameter of the moon. So this becomes basis. AB becomes the basis. So for my same formula I have to change, so I will get diameter AB or basis equal to S theta. Because you know theta is arc length upon radius. So theta is what is the arc length? Now this is the center and this is my arc. So arc length is my diameter AB and S is the distance, this radius. So you transform the side, you will get AB equal to S into theta. So knowing this formula, you can calculate the diameter of the moon. Is it all right? So revise various formulae that we derived today and in the previous session, so that we can do the numericals. If you have not subscribed so far, you can subscribe to the channel and like the channel, press the bell icon so that you will get notification when new video is posted in YouTube. Okay, thank you very much.